Hi all. This is a quick example of Faraday's law, and we're going to look at a rotating loop. So you might spend a second copying this down and pausing, but basically here we've got a loop and it's going to rotate in this magnetic field, and we're going to give it a frequency. The magnetic field is B or B naught, and the area is A naught, and those aren't going to change, but the angle is going to change. And it's going to look something like this, and I'm going to shoot over to an animation. So between these magnets, there's a magnetic field that goes from the north to the south, so it's up, just like in the picture we drew. And we're going to rotate this loop of wire. And if you watch, you get a voltage. And that voltage changes with time. And this is what we call alternating current, by the way. It's what ComEd generates for us. And you'll notice that the current reverses every half turn of the coil of wire. Okay, so that's what we're kind of calculating here. And we're going to start with Faraday's law. Well, first we got to actually find the magnetic flux. So let's actually start with that. So the magnetic flux is it's technically the double integral B dot dA, but in this case it's BA cosine of the angle. Okay, now the angle is what's changing with time. Okay, the angle is equal to omega times time. Okay, now let's assume that we're starting in this position, so the area vector is pointing parallel to the magnetic field, which is pointing up. So they're both pointing up, so the angle starts off at 0. All right, and so then technically the angle is omega t plus omega naught, but omega naught 0. Okay, so this is a good review of stuff from the first semester right there. Okay, now I didn't give you omega, I gave you F, frequency, 60 hertz. Now we're not going to plug a number in, we're just going to call it F. And that is, by the way, the frequency that ComEd does generate at. So if you remember, omega is 2 pi F. In other words, for every one cycle, you're doing 2 pi radians. Okay, so this becomes 2 pi F times T. Okay, and this is what we're going to plug in for theta. So you get magnetic flux is BA cosine of 2 pi Ft. Okay, now Faraday's law, EMF is, and I'm gonna skip the negative for now, but it's d magnetic flux dt, the magnitude of the EMF. Now, if you look up at this equation, the only thing that's changing is the angle is a function of time. So the b and the a are constant. The derivative cosine is negative sine. So we got negative sine of 2 pi Ft times the derivative of the inside of that, which is 2 pi F. Okay, your dt, which should go over here, is actually over here, so we've got it taken care of. So the EMF as a function of time, and again, there's a negative in here. I'm going to lose that because right now I just care about the magnitude. And I'll put this stuff out front. So you get 2 pi F BA sine of 2 pi Ft. Okay, so that's the EMF as a function of time. You notice the sine curve, and you'll notice that on here when you play this, it's a sine curve. This is definitely a sine curve. Now, a couple notes. On a problem like this, be careful. You'll see in the book, you might see a problem where they give you, for instance, they'll give you the B, they'll give you the A, okay? And then they'll say something like this. They'll say d theta dt equals 60 degrees per second or something like that. So this is really close. What you need, though, is you need this in radians per second, and that would be 2 pi F. So what you want to do is convert the degrees per second to radians per second, and that would be your 2 pi F here. Or if you convert it to revs per second, that is F here. So you can do it either way. So just make sure you're putting the right units in for this. All right, I hope that example was helpful, and good luck on the next one.